This is a presentation on the case history of the capacity of a drilled shaft in the Atlantic coastal plain, done by Matthew Holtschneider, Kyle O'Malley, and Brendan Schiaffo.
Some background knowledge of the geology of this report is that it was located in the Atlantic coastal plain, which spans from New York City down to the coast of Florida. The northernmost part takes up was present-day Long Island, Staten Island, and southern New Jersey, and the upper levels of the soil are made up of mostly fluvial sand, gravels, and some clays that were deposited here from 150 million years ago due to changing ocean levels and glaciers.
So the site for this project is found in south central New Jersey, and there is a sand layer which goes up to 45 meters below the surface, and then there's a diatomaceous clay which is 70 meters thick, and a Paleozoic bedrock which is found around 1,400 meters below the surface.
So the strategy behind testing this site is first you want to take a test bore, and the test bore location is going to be chosen close to the shaft where it's actually going to be, and we're going to be using the standard penetration test to obtain and observe data. Then after that you want to install the observation well, and once the observation well is installed, you want to wait a couple of days to record water levels to make sure that the borehole is stable. After this you want to do some lab tests, but however on this site there was already previous lab tests done. This way, no additional testing was needed. You want to apply all correction factors for anything like overburden pressure, and hammer energy. And then once you find these corrections, you can plug them into the N60, which is the number of blows, times the hammer correction, times the bore correction, times the rod length correction, and the sampler correction. Once you have the N60 value, you can then plug it into your N160 value, which is the overburden correction factor times the N60 number. Once this is done, you can derive all axial capacity stresses from these equations. This table corresponds all hammer corrections and overburden pressure corrections for our N160 value for each depth according to the test strata. Some of the soil properties predicted from the site, from the testing, is that from the axial stress, that from all the corrected values, that the soil bore had relatively high N values. This can most likely be because the sand is difficult to use because there is little to no cementation. The poor water pressure in the sand also affected it due to its dilation. These issues further complicated the data from these test results.
To create the test, they had to construct a test shaft. This included vibrating a steel pipe casing to a depth of 10 meters below grade. The casing was 1.372 meters by 12 meter in steel piping. Once that was in place, a single flight auger excavated to 33.1 meters below grade. After that, bentonite slurry was placed in the hole to help stabilize the excavation, and a reinforced cage, including equipment with the Osterberg cell, assembly was lowered into the drilled shaft. Concrete was then poured into the drilled shaft using the Tremie method. The Tremie method is pumping concrete into wet concrete. According to AASHTO, there are 5 different procedures for nominal side resistance drilled shafts into sands and 4 different procedures for nominal end bearing resistance into sands as well. The predictions for nominal end bearing resistance are calculated using the side resistance predictions to find the total nominal axial resistance.
This table shows the predicted axial capacity for the Toma and Reese in 1974, and includes the depth, the stratum, total stress, and effective stress. This table shows the predicted axial capacity for the Meyerhof in 1976, and includes the standard penetration test values and the shear strength. This table shows the predicted axial capacity for the Quiros and Reese in 1977, and it also shows the depth, standard penetration test values, and the shear strength. And on this table, we have the predicted axial capacity for the Reese and Wright procedure in 1977. And as you can see from the table, we have shows the shaft diameter, standard penetration test depth, the values of the standard penetration test, and the shear strength of it. And here is the predicted axial capacity from the Reese and O'Neill in 1998, which includes the depth, total stress, and effective stress.
So the Osterberg cell load test was done with a 533 millimeter cell. And then there was also successive loading, which the loading increment lasted for 4 minutes. And the data logger logged over 30 different increments, where the max bidirectional loading was 8.95 meganewtons. The loading was stopped when the shear capacity approached the max capacity. On the left here, you can see the test shaft elevation diagram, which had 5 different stratums, as long as their depths and their thicknesses. On the right is just a picture of the Osterberg cell setup with the data logger all the way on top connected to the shafts that are lowering down the O cells. So interpreting the load test, the maximum net load, according to Simpson in 2003, was 8.22 meganewtons. This maximum load was upwards at the top of the O cell. The total deflection from this was 29.9 millimeters, or 0.299 meters. The maximum load applied downward was 8.5 meganewtons. This downward movement caused the cell base to move 116 millimeters, or 0.116 meters. The maximum applied unit end at the bearing pressure ended up to be 5,370 kPa. Table 7 shows the net unit side resistance acting on the drilled shaft segments, which refers back to Figure 1, which was the diagram of the O cell with all the stratums and the depths. This diagram here shows the load versus displacement for the O cell test. As you can tell from the diagram, that the more load being applied downward, the more movement of the soil there was. You can also see from here that the more load, the more movement there was soil moving upwards towards the top of the O cell.
This slide is on the comparison of the predicted values versus the observed for the side resistance. And the way that they computed the predicted values is by using the strain gauge data and the estimated drill shaft stiffness and the shaft area from the static test. And if you look to the diagram on the left, this bold line right here with the squares on the corners, that is the observed value. And as you can see, for the AASHTO procedures, over predicted the nominal side shear resistance through stratums S1 or C1 and S2, and then they under predicted for stratum S3. This slide is the comparison of the predicted versus observed values for the nominal and bearing capacity. And as you can see in the graph to the left, the observed value is the one all the way to the right, and all the other values on the left are way over predicted for it. And the way they found the observed value is by the total nominal axial resistance minus the side shear resistance, and that ends up to be 2.52. And what this value represents is the mobilized end bearing capacity of the shaft under the applied load at which the load deformation behavior meets the definition for nominal axial capacity. This is the comparison between the predicted versus observed for the total axial capacity. And as you can see in the graph to the left, they are again all over predicted for the total axial capacity. And this is found by finding the side friction and the end bearing capacity and then combining the two.
In conclusion, the prediction of axial resistance in Atlantic coastal plain sands widely varies. almost all of them, or all of them, were overestimated in the total nominal axial resistance. Therefore, it is very important to use the Osterberg load test to verify the axial capacities.
So that brings to the conclusion of our capacity of a drilled shaft in the Atlantic coastal plain. We would like to thank Dr. Weaver for viewing our presentation and supplying us with, with the paper for this project. And attached, you will be able to see our sources. Thank you.